Number 4, a football coach sits on a sled while 2 of his players build their strength by dragging the sled across the field with ropes. The friction force on the sled is 1,000 newtons and the angle between the 2 ropes is 20 degrees. How hard must each player pull to drag the coach at a steady 2 meters per second?
Okay. So you start out, you just draw your picture. And you just go from there.
Angle between the 2 ropes is 20 degrees. The friction force on the sled is 1,000 newtons. So, free body diagram. $1,000 newtons. That's a lot.
Mm-hmm.
And yeah, we have our normal force and gravity and 2 kids. Okay, I drew it.
Okay.
I don't know what to do now. So I hate this part. I need to figure out how to do it though. So, sum of the forces equals mass and acceleration, and the y and in the x. So, they both need to equal the y and so what do I do with the 2 meters per second? I feel like that's what we need to end up with, so I need to be setting something equal to that. Is that right?
Let me see. So, what is the 2 meters per second?
It is the velocity.
Okay. And it's a constant velocity, right?
Yeah.
So if our velocity is a constant 2 meters per second,
Then they need to have an equal force as the friction.
right?
Is that right?
Yep. So, oh my goodness. Okay. A lot of times they'll give us like velocities. So they're trying to trick you, and they say the velocity is 2 meters per second. But what equation relates force and velocity? Do we have one? Right, none. We just have this one.
Acceleration, but there is no acceleration.
Right, because it's going to constant velocity. So we know that in the end, force is going to be equal to mass times acceleration, which is 0. So our net force on the sled has to be 0. Okay.
So that's what they want you to get from that.
Mm-hmm.
Oh, that's rude.
But they'll try to trick you all the time. But you just remember, you say, no, I know better. Force equals mass times acceleration.
Okay.
It talks about equilibrium in the book. And there's 2 kinds.
Yeah.
There's static equilibrium, which is where it's just sitting still, and then there's dynamic equilibrium, where it's going at the same velocity. And you can kind of feel that, like, naturally. If you're going down the road, you're like sitting in your car, you have the cruise control set at 75 miles an hour, does it feel like you're moving?
No.
Not really. Like, you look outside and you see everything going by, but as you're just sitting in your car,
Yeah.
going a straight line, just sitting in your car, your body doesn't feel like it's moving. But when you sit in your car and you pull off from a stoplight, then it does feel like, because you kind of push back into the seat, you can feel,
Yeah.
you kind of have to adjust yourself to accommodate for that motion.
Uh-huh.
So that's because there's forces at work when you're accelerating from the stop sign or the stoplight. But when you're just going at a constant velocity, it doesn't matter what velocity you're going. You can be going 75 miles an hour. On a plane, you're going like 600 miles an hour, and it doesn't feel like you're moving.
Yeah.
Yeah, you feel like you're in a room, you know, you like walk back and forth along the aisle of the plane, you just feel like you're in a building. That's because there's no forces at work. It all equals out, it's an equilibrium, even though you're going 600 miles an hour. So they'll try to trick you with velocities all the time, but don't fall for it. Okay?
Okay.
Let me know that we've got our 2 tensions from the ropes, we got 1,000 newtons. I'm gonna leave off gravity and
Normal.
and normal force, yeah. Because this would actually be like from looking above. Because you'd
Yeah.
have the coach sitting on the sled and then the 2 kids would be spread out this way, pulling this way.
And then the other two will be pointing at you
Yeah,
in the other direction.
so it's kind of harder to sum those ones. Right?
Okay, so that means that the sum, do I need, so what I'm thinking is that we need to have the x and the y components be equal to 1,000 newtons. Is that right?
Mhm.
Because if the acceleration is 0 and it's a constant speed, they come out to be equal, right?
Yep.
So would all the y components and the x components have to both come out to 1,000, or do they need to both come out to 500? Or does just the x need to go 1,000?
So why would it be that one?
Because it's the x direction that's going negative 1,000 and not the y.
Yeah, so this 1,000 newtons, when you sum your forces, it'll only show up in your x equations. It
Okay.
never shows up in your y equations. And that's because when you break these down, you're gonna have 2 going down the middle, right? And you have one going this way and one going this way.
Mhm.
Those 2 will cancel out for you.
Okay.
Just like on that speaker, we had our x components went like this,
Mhm.
but they just canceled out for us.
Only because what we were looking for was in the y, right?
Mhm.
Because you could say the same for, because the length of the chords was equal, and the
Right.
y's could cancel out too, but, well, not really, because they're not negative and positive, they're both positive.
Right, so the y's were the same, that's true. Just like this one, the x's will be the same value because the angle is the same,
Mhm.
so.
Okay, so now we need to sum the forces of x.
Okay,
Sum of f of x. So we do not have an angle. Yeah, we do, it's 20 degrees.
so this whole angle right here, 20 degrees.
And could you just split that in half?
Yeah, I think it says that there. Yeah, I mean, it doesn't say specifically that they're equal, but
But
it's saying how
does that
much
matter?
does each player. Well, it would matter if you had one player, say it was like this, one player was pulling harder and the other kid was just over here, kind of goofing off or whatever, like he's kind of pulling, but then it would matter because they would have different forces.
Uh-huh, but the addition to both of them will be the same,
Mhm.
right?
So if it's saying how much does each guy have to pull, that's assuming that they're pulling equally. So I would do it with 10-degree angles in between.
Each player.
So they're not really asking a question like this. Besides the fact that if they were both pulling equally and it was down like this, what would start to happen?
If they were both pulling equally,
And like, it was tilted like this rather than being straight on?
then it would change into Y.
Right, so it'd start turning that guy. So you just assume they're pulling in a straight line. Okay.
All right, so then we still don't have much, but we want to find the one in the middle, right?
Mhm.
So that is adjacent.
Let's call this T.
So we want adjacent equals T. Man, I used to know these so well and I don't remember anymore. It's cosine.
Mm-hmm.
Cosine of 10. And just, would you do another one plus T cosine?
Mm-hmm.
10?
Because you got one for this one, and you need to add this one.
Okay. And you don't minus anything, right? Because there are no other X components.
Right, what do you have so far?
That.
Well, which one is still in the X?
Which one's still in the X?
Mm-hmm. It's a big one.
1,000 newtons.
Yeah.
Only that's what would make it. Do we subtract that?
Right, because it's going this direction.
Oh.
So these ones are pointing to the right, and the one that the friction is pulling back.
Okay.
So this is what, and if you didn't subtract one of them, then you wouldn't have, they'd all have to be zero, right, in order for it to be zero?
Mhm.
Because if you add anything, like, no matter how small this number is, if you add it to another really small number, and then add it to another really small number, it's still not gonna be zero.